Okay, and our next speaker is going to be talking about what I think is a super interesting topic, water and wastewater treatment, which apparently you can make all sorts of decisions about how to approach this through CVXPY, which was a complete shock to me when I found out about this. And so I'm super enthusiastic to hear more. So I'd like to welcome up Daly Wettermark.
Yeah, you never have to ask more than once to get our lab water in this bottle. We love talking about it. And yeah, so our lab is in environmental engineering. Hi everyone, my name is Daly, and I'm a PhD student in the Wettermark lab. I'm making water. And yeah, we're an environmental civil engineering lab made up of a lot of engineers from various disciplines, mixed levels of optimization and computer science background, but are very interested in applying all of these tools to energy flexibility and water infrastructure. So as a little bit of motivation, water and wastewater systems are really large energy consumers. So across the globe, there are estimates that they consume around 4% of global electricity, which vary regionally based on how much pumping is used, based on the level of treatment is carried out. And these facilities themselves are acutely aware of the energy they're consuming because it accounts for somewhere between 1/4 and 1/2 of their OpEx. So they're paying attention to their energy costs. And we also know that increasingly electricity prices and emissions are quite variable, both spatially and temporally. So in California, for example, we have increasing fractions of renewables, which is critical for decarbonization, but also creates duck curve-like shapes in both the availability of things like solar throughout the day, and also the emissions factor of energy from the grid. So here, for example, we see that in the middle of the day, the emissions factor, which is on the y-axis, is kilograms of CO2 equivalent per unit of energy consumed, is lowest in the middle of the day. Solar is after. And for a combination of reasons, including where the energy is coming from, as well as the demand is placed on the grid, we also have a lot of variability in electricity prices. Oh, yes, absolutely. So, yeah, it tends to be in the late afternoon to early evening hours that there's a lot of demand placed on the grid, and electricity prices tend to be a lot higher. That's not something that the typical household consumer will see, because a lot of times our energy prices at home are fixed just based on the kilowatt hours we consume. But it is something that larger industrial energy consumers like water and wastewater treatment plants see, because they're on an industrial electricity pricing scheme that's actually charged based on the time of use of when they're using the energy throughout the day. So this poses a really interesting kind of time series modeling and optimization problem that our lab has been interested in looking at across a lot of different water infrastructure types. So I'll be mostly focusing on wastewater in this talk, but we'll allude a little later to some of the other water processes which my other lab mates, a lot of whom are sitting in the back here, work on. So for the wastewater treatment example, we have a wastewater treatment plant which is taking in sewage from a sewage network and is also taking in energy from the grid, both electricity and also gas that they're purchasing for running things like boilers and for generators on site. The wastewater treatment plant will often produce biogas, and this is a methane gas that's a product of the solids treatment at the facility, and then use that biogas together with some gas from the grid to produce electricity on site, and use that to sustain some part of their load. So the first part of creating an optimization problem for this facility is to actually build a model of the electricity consumption. So we've done that with some partners that we have, wastewater treatment plant partners, to try a few different mechanisms for fitting models to the electricity consumption of the facility. For example, we've been typically using an ARIMA X model, which uses autoregressions of both the electricity consumption itself, as well as the influent flow of wastewater, and then forecasting and modeling the electricity consumption based on that. So once we have that model, the other key variable option that we have at facilities is storage. So things like storage of the wastewater itself, storage in a battery of electrical energy are things that we can use to meet some of the facility's load and change the timing that we're actually purchasing from the grid. So then implementing that into an optimization model, this does end up being a linear problem. All of the models that we're fitting are either linear ARIMA X or least squares or other types of linear fits. So we end up with a model that is based on two key operating variables, one of which is this X and T, which is the electricity consumption purchases from the grid at a given time. The other for wastewater treatment plant being Y, which is fossil gas consumption. And then to those, we add various factors for both the costs at the different time of day, as well as the emissions factors at different times of day, depending on the exact asset. I'm not going to go too much into detail here because my lab mate Fletch is going to be giving a talk more on an actual package that was spun out of this problem that can be used for any electricity consumer, not just water or wastewater. So stay tuned for more on that at 2:45. So then to that objective, we subject it to various constraints about operating the facility. So the underlying electricity model that we fit, as well as mass balances and operating balance of the equipment that we're operating at the facility. So this is what the output of the time series optimization might look like for a given set of, this is a 5-day example for the wastewater treatment facility. So in the solid black line, we have, the dotted black line, we have the baseline electricity purchases from the grid for this facility. And you can see that, for example, in the middle there's a couple of times when it shoots up and has a peak. And then in the gray shaded areas that are labeled daily time of use periods, that would be that 4 to 9 p.m. period of the day when prices are a lot higher. So in the optimized curve, which is in the solid black, that is what the CVXPY optimization is returning for the recommended electricity consumption profile that this facility could use if they're leveraging the flexibility they have inherent to the storage that they can do wastewater, the battery, so they can do, and how they can change the timing of their consumption. So based on that, we can do things like generate operating set points for operators at the facilities and tell them at a given time how much natural gas from the grid do we recommend that you purchase, how much do we recommend that you put in storage at a given time, and make those recommendations to facilities. So one facility that we've worked with in the area, Silicon Valley Clean Water, for example, they actually have an existing cogenerator and an existing battery on site. They've been using sort of some more heuristic methods for operating the cogenerator and then using a third party to actually operate their battery that didn't have insight into their full facility operations the way that we've included. So when adding in the total modeling of the system, we're able to get a mean monthly benefit of around 8%, or in some months up to like 15-20% savings on their electricity bill by doing this integrated decision making. So just to know that there's some other elements that we can add to this problem. For example, demand response revenue from demand response programs that will actually pay consumers to reduce their load if there's a really high stress moment on the grid. There's also something that I've been working on, which is the ability to optimize the exports of electricity from a cogenerator facility back to the grid, which is, it goes back to the Boolean capabilities of CVXPY. So I'm interested in looking more into that. And then something that we can also include is including capital decisions and design decisions. So we've been using sometimes like another layer of optimization on top, like a grid search or a lazy 3D search to size the battery. But then my lab mate Akshay has also been looking into kind of including it in the objective function itself and kind of combining this all into a single optimization. So those are all different flavors that we can add to this. I think I only have another minute or two next, so I'll just quickly mention that we've also co-optimized for both emissions and costs. This is from some work that Fletch led, and we did a series of multi-objective optimizations that produce these creative trade-offs to show how a facility can jointly optimize both electricity and emissions. And then, yeah, some other work that is done across the lab. This is sort of a paper my lab mate Akshay, showing how different types of water facilities can be represented. We use a variety of different tools, some Hyomo and some other modeling tools, depending on the level of resolution we need in these water system models. But CVXPY is definitely a big element in how they're included. So this is an example of showing that if we're looking at the overall value of energy flexibility, we could see that, for example, advanced water treatment actually has like kind of a more clear NPV positive value just in the inherent flexibility of the system. And then wastewater, it's actually more dependent on the tariff structure, whether or not we're seeing a direct benefit of flexibility. So yeah, with that, I want to thank all of the collaborators who've been working on this mix of work in our lab. I'm happy to chat more over lunch or get to get more of y'all's thoughts. But yeah, you all very good.
Sorry, a little behind. I'm gonna take note of questions. Apologies. Thank you so much. It was a little while ago that I was talking to somebody from the W3 lab and found out that they were using our library for such cool stuff. So I've always been a huge fan of hearing about the work there. Our next speaker, Tabia Markushi, is a professor at UC Santa Barbara, did his PhD at MIT, and did a number of visiting scholar positions here at Stanford as part of that.